Okay. So the last thing we talked about, or I talked about it on Monday before we left, was this graph. Okay? And I use this graph to show you what makes things stick together better. Okay? So just the big ideas that I would take out of this. Big ideas I would take care of this. Since those are all nonpolar, this increase is because of dispersion forces. So everything should have an increase as you get bigger because you have more electrons and dispersion forces get stronger. So you'll know the general trend is always this way, right? So the reason why PH3 has a lower boiling point than ASH3 is because they're both polar, but ASH3 has more electrons than PH3. Because AS has 33 electrons, P only has 15. So the total number of electrons is different. And that's going to be the true all the way up all of those lines. If there's a general trend, they increase, the bigger the molecules. So big molecules tend to have higher and lower melting points. When you're comparing here, these are about the difference between being polar and nonpolar. The reason why SiH4 is not as stuck as PH3 is because SiH4 is completely nonpolar, PH3 is polar. So this little jump here is about being polar. All of these are a little bit higher than the flat line because the flat line is nonpolar, then there's a little bit polar, then a little bit more polar, and then even more polar. So they stick together a little bit better as they become more polar. So that's about dipole interactions. And then over here, we got these three up here that are way off the chart. They should be down at the bottom. If I was worried about just dispersion forces and dipole interactions, they should be down here. But they're not, they're up there because this huge jump is about the fact that this can hydrogen bond. This big jump is because it can hydrogen bond, and water's really big jump is because water can hydrogen bond twice. So if you can hydrogen bond twice, you're going to stick together better than if you can only hydrogen bond once. So that's what I was trying to show you with this graph. It was about how being bigger makes dispersion forces stronger, how being polar makes the intermolecular force stronger, and how having hydrogen bonds makes it really strong. Because this one with the water, it has dispersion forces, just like the ones below it. It has dipole interactions, just like the one below it. It also has hydrogen bonding. Right? It has all three. It's going to stick together better. So making those decisions. So HF, what kind of intermolecular force would HF have? Say, it's not fair, Mr. Green, I don't have an electronegativity table. I'll give you some electronegativities. H, 2.1. F, 4.0. Okay. So can HF do London dispersion forces? Well, what causes London dispersion forces is electrons, right? Electrons moving around. Does HF have electrons? Yes. So it can do London dispersion forces. Is HF polar? It's got polar bonds and it's not symmetrical, so since it's polar, it can do dipole interactions. Can HF hydrogen bond? Does it have H hooked to F, O, or N? Yeah, it does. It has H hooked to F, so it can do all three. So HF would stick together pretty well. Has strong intermolecular force. About the F, F is 4.0 in electronegativity, and the next biggest one is 3.5. So if F is hooked to anything, it's a polar bond. Because anything you put it back next to is going to have a difference of bigger than 0.5. Because the next closest, it goes 4.0 and the next one's 3.5. You're automatically polar. So fluorine's so electronegative, no matter what you attach it to, it's going to pull the electrons towards itself. It's a strong, greedy one. Oh yeah, if it's hydrogen bonding, it's got to be everything else too, because the way you get hydrogen bonding is because it's polar. Okay? And the way you make it polar is to have electrons. Okay? CCl4. And carbon is 2.5, and chlorine is 3.0. Does CCl4 have electrons? Yeah, so it can do dispersion forces. Everything can do dispersion forces. Is CCl4 polar? Well, it's got polar bonds, but that's not enough. We've got to check the shape. Okay. CCl4, to put 4 Cls, I'd have to put 4 bonds, right? And that shape would be 4 atoms with no lone pair around carbon, and 4 atoms with no lone pair would be tetrahedral. So it's Cl, C, Cl, Cl, Cl. So it's got polar bonds, but is it polar? It's got polar bonds, is it polar? Well, if you look at that, so the white spheres would indicate the Cls, and the black one would indicate the carbon. The Cls are going to be negative because they got the bigger electronegativity. Where are they at? They're all on the outside. So the outside's negative and the center's positive. Does that describe a polar one? No. So all CCl4 can do is dispersion forces. If it's not polar, it can't do hydrogen bonds. Yeah. What? Do I subtract to figure out whether this bond is polar? It was. Okay, because that's bigger than 0.5. 0.5 or bigger. C is 2.5, Cl is 3.0. That's a difference of 0.5. All the bonds are polar. Okay, so then I have to worry about the shape. In order to be polar, you got to be a non-symmetrical shape. That's a symmetrical shape. So that's non-polar. So the answer for this one is it can only do dispersion forces. No, see, that won't happen because they got the same charge. So it can't do dipole interaction. It can't put 2 poles together. It can't put this carbon next to that chlorine. You can't do it. So it can't do dipole interactions because it can't get them together because the negatives would run into each other. Does that make sense? So it can't be dipole interaction. Can't be dipole interactions because it's nonpolar. It doesn't have an end. It doesn't have a positive end, doesn't have a negative end. It's got a positive middle and negative outside.
So does that mean the bond's polar, but the molecule is not?
Yep. Okay, remember, polar bonds is just a subtraction problem. Polar molecule is polar bonds plus shape. So anytime you want to figure out whether it's polar or not, you've got to figure out what shape it is. Well, I know, you don't have to figure out a shape. Once you do the subtraction, if it's too small, you don't have to worry about the shape. And if it comes out to be 0.2, it's nonpolar. You're done with dispersion forces. Okay, so that gives you a better idea of how to do number 2 on the back. Here's a hint. You should circle London dispersion forces often. This is because it says circle all the intermolecular forces it could have. Right? NF3. N is 3.0, F is 4.0. Does this have dispersion forces? Well, dispersion forces are caused by electrons. Does this have electrons? Yeah. So it can do dispersion forces. Does it have polar bonds? Yeah, that's a difference of one. So now it's got polar bonds. I have to worry. It might be polar. Depends on the shape. Okay. So I've got nitrogen hooked to 3 fluorines. That gives nitrogen the 3 bonds it wants to make. And the fluorines the 1 bond they want to make. Right? Then I got to fill up the dots. Each fluorine needs 6 more dots. So that's 24 more dots I'm adding. Or 18 more dots. And then 2 more on the nitrogen is 20. And then 6 more is 26. And I had 3 times 7 is 21. Plus 5 more is 26. I got the right number of dots. So this is the right structure. If you're going to go by bonds, at the end, you got to count total number of electrons to make sure you didn't just throw some stuff in that made it look nice. So this has got 26 dots. I only had 26 dots when I started with. Okay, so these bonds are polar. What shape is this? Well, it's got to be a triangle because it's got 3 F's. Flat triangle or pointy triangle? What would make it pointy would be lone pair. Does this have a lone pair on the nitrogen? Yep. So if I drew this, it would be trigonal pyramidal, right? The N would be up top and all the F's would be at the bottom. The N would have a positive charge because it's got the smaller electronegativity. The F's would have negatives. Is this polar? Yeah, it's got a positive top and a negative bottom. So we can do dipole interactions. Can it hydrogen bond? Does it have hydrogen hooked to nitrogen, oxygen, or fluorine? No. So it can't hydrogen bond. So this would be dipole interactions and London dispersion forces. No, you do each bond separately. 4 minus 3, 4 minus 3, 4 minus 3. I'm checking out this. Checking out that right there. This is a 4. This is a 3. The difference is 1. This is a 4. This is a 3. The difference is 1. Do each bond individually. Now you don't take fluorine and multiply it by 3 because you're not hooking all 3 fluorines in the same spot. Okay? So each bond is separate. Okay. Other questions? Okay. All right, so just a reminder about last chapter. Because this is the end of our talking about the different kinds of compounds. Well, not the end. We're just not going to introduce any new ones for a while. Okay? So ionic compounds, we're going to recognize that they're ionic because they got a metal and a nonmetal, a loser and a gainer. Okay? This is the ones where you draw arrows showing the electrons moving from the metal to the nonmetal. Sodium gives its electron to chlorine, so you get a positive charge and a negative charge, and they stick together. Solid ionic compounds do not conduct electricity. But they're good conductors when they're made to turn into a liquid when you melt them, or when you make aqueous solutions. Aqueous means dissolved in water. If you dissolve them in water, the light bulb comes on. You did the lab where you tested that? Let's try to see if they dissolved. If they dissolved, the light got bright. If it was ionic, sugar dissolved, the light didn't get bright because it wasn't ionic. Salt made the light bright, sugar didn't change the light. Okay, these are going to have high melting points. You put them on the hot plate, you put salt and and 5 other things on the hot plate, the salt never melted. So since they have high melting points, you never see them as liquids. The only time you've ever seen them as liquids, I showed you the crystal growing as it turned back into a solid. watch the crystals grow on screen. And what's holding those crystals together is ionic bonds. And ionic bonds are going to be a lot stronger than intermolecular forces because intermolecular forces are temporary. And the charges are partial. Okay. Ionic compounds got full charges, and they're permanent. So they're going to stick together a lot better. So that makes them hard, and it makes them brittle. They don't bend, they snap. You can't flatten them out, they crush into a bunch of powder. So that was the chapter 7 stuff. That's what happened when you transferred electrons. What do you get when you share electrons? Well, first of all, the ones that are going to share electrons are going to be nonmetals or nonmetals and hydrogen. These are also going to be bad conductors of electricity. But they're always bad conductors of electricity. They're always insulators. Doesn't matter if they're solid, liquid, or dissolved in water. Doesn't matter what you do to these. They won't conduct electricity because they don't have any charged pieces. To conduct electricity, you have to have charged pieces that can move. Molecular compounds, nothing has a charge. You don't have any charges, you can't move them around separately. So you can't conduct electricity. Molecular compounds tend to have low melting points. 99% of them have low melting points. We'll talk about some exceptions in a minute. What do I mean by low melting points? I mean that every compound that you've ever seen that was not a solid, either a liquid or a gas, was molecular. H2O, nonmetals and hydrogen. Carbon dioxide, 2 nonmetals. Gasoline, C8H18, nonmetals and hydrogen. Rubbing alcohol, C3H6OH, H7OH, sorry. C3H7OH. A liquid, okay, because it's made up of just carbon, hydrogen, and oxygen, nonmetals and oxygen. Okay. Now, there's 2 kinds of crystal. Almost all of it does one, and then there's some specific ones that don't. And one I'm going to be able to ask you to predict, the other one I'm not going to be able to ask you to predict. I'd have to tell you that's what it was. Okay, so the molecular solids, like you pick up a crystal of sugar, that means sugar molecules are hanging on to sugar molecules. Okay, and what's hanging one sugar molecule onto another sugar molecule is sugar can hydrogen bond. And most molecular solids are that way. And they're held together by intermolecular forces, which are much weaker than real bonds. That's why they melt easy. That's why they boil easy. It's because they're not held together very strong. But then there's some that are held together strong, and those are called network solids. And in a network solid, it's a network. A network means everything is connected to everything else. Right? So a network means everything is connected to everything else. Well, in a network solid, there are no intermolecular forces. It is all real bonds. Everything is bonded to everything else. It's one big long chain. So in order to get it apart, you actually have to break real bonds. So network solids are going to be held together much better than molecular solids. So it's a compound where every element, compounds and, it should say and elements, I don't know where my D went. Compounds and elements, where every atom is covalently bonded to other atoms. So we're not talking about intermolecular forces. So you can think of them as one big molecule. Or we're used to putting numbers like 2 or 4 or 7. We're talking billions and billions of atoms all hooked together. So if you pick up sand, those little tiny crystals in sand, most of them are quartz. And quartz is SiO2. But that's just in general. That means there's 2 O's for every Si, because its structure looks like that. They built it out of the balls and sticks that you built. And what would happen is you can see that every silicon is hooked to 4 oxygens. And those 4 oxygens can hook on to 2 silicons apiece. So this one right here, there'd be another silicon that could hook on here. There'd be another silicon that could hook on here. Every one of those oxygens that doesn't have a silicon hooked to it would have a silicon hooked to it. It would all be hooked together to one big molecule. As it grows, you just add, if a silicon adds an oxygen adds a silicon. Okay? So you get one big stuff. So when you tried to melt the stuff, sand didn't melt. Because in order to melt it, you'd have to break all those bonds. And real bonds are much, much stronger than intermolecular forces. So to melt sand, like you do to make glass, you got to get up to 2400 degrees before it melts. So quartz is a compound that makes a network solid. Okay, so here's a 3D representation of it. So they've got this silicon hooked to 2 oxygens, which would hook to 2 more silicons, which would hook to 2 more oxygens, which each would hook to 2 more silicons. Works out that for every silicon, there's 2 oxygens. Okay? So that's what the unit is that repeats. Okay? It's the unit that repeats. So there would be 3 of them hooked together, repeating. Here'd be a whole flat piece of it. But you can see you got a flat piece, but I got silicons up here that need to hook to stuff, and I got silicons down there that have only made 2 bonds. The silicon's got to make 4 bonds every time. Oxygen's got to make 2 bonds every time. So what you end up with is this, which every cube, every oxygen's hooked to 4, and this is all one big molecule. Everything hooked together. Okay? And it's why it's hard to melt is you have to do that. And it's also why, if you ever see a big piece of quartz, it's always a hexagon. See those crystals hanging from people's mirrors in a car? Those are quartz, and they're hexagons because this shape has weak areas, weak directions. See, it's weaker this way than this way. You have to break fewer bonds going on that diagonal. And it turns out the angles there are just right to make everything a hexagon. So it only grows and breaks at certain angles because there's angles built into every one of those bonds. Okay? So that's what silicon dioxide looks like. Okay? So in sand and quartz, it's all nicely patterned. But in glass, what they do is they heat it up and they don't let it make, and then when they cool it, they don't let it make the pattern. They put other stuff in that makes it so it can't make the pattern. Okay? That does two things. A, it makes it clear because there's no pattern to break up all the light. If there's a pattern, light's going to get broken up by that pattern. But since everyone's a little bit different, there's no going to be one way everything's broken up. The second thing it does is the window doesn't break at any specific angle because it's just randomly arranged. Those chains are just randomly hooked to each other, not in a pattern. So when you break glass, it breaks in every direction. It doesn't break in a certain direction. If you break quartz, it breaks in hexagons. Okay? All the time, every time. Okay. Diamond. The formula for diamond is C. That's its formula. It's just pure carbon. Okay. But it's pure carbon. It's pure carbon. But there's what it looks like, and what it is every carbon is tetrahedral. Okay? And they all line up in a nice little hexagon pattern. Okay? The carbon-carbon bond is really strong, and it makes 4 of them every time. So it's hard to break these carbon atoms away from each other. That's why carbon is the hardest material. Is in order to take a chip on it, you've got to break the covalent bonds, which is tough to do. But even though it's the hardest material, you can cut it with something softer. Although you don't actually cut it, you break it along those angles. So you can take a piece of steel and hit it at just the right angle, and a chip will come off. That's what diamond cutters do, is they chip at the right angle. So if they chip at the wrong angle, that big diamond turns into a pile of dust. Shatters. Because instead of breaking right along here, you've caught a bunch of bonds. It tends to make the thing shatter. Okay? So they got to be careful when they're cutting diamonds. But there's a correct direction to cut them. One big molecule. Everything's bonded to everything else. That's why diamond's hard. That's why diamond has a really high melting point. Because I think the diamond melting point up there is 4,100 degrees Celsius, which is probably 7,000 degrees Fahrenheit. It's held together really well. Question?
No.
Okay. I respond to hands. I'm a teacher. We do that, right? Okay. Then there's graphite. The formula for graphite is C. Say, whoa, whoa. So if I buy graphite, the stuff in my pencil, I'm buying pure carbon like I was buying diamond. So why spring for diamonds? Well, because graphite has different properties than diamonds, even though they're both pure carbon. Okay? Because graphite, where's my arrow? In graphite, every carbon is hooked to 3 carbons in a trigonal planar. And if you got trigonal planar, hooked to trigonal planar, hooked to trigonal planar, you get one big flat sheet. Right? One big flat sheet. And that one flat sheet lays on top of another flat sheet, lays on another flat sheet. Okay? What's holding these sheets together is intermolecular forces. And those are easy to break. So when you're writing with a pencil, what you're doing is you're wiping layers of graphite off, because the layers aren't hooked to each other, except with intermolecular forces, and they can slide right off. That's why you want to use graphite if you need to lubricate a lock. You don't want to put anything wet inside a lock, because any dust that gets in there will get stuck. So you want to put something dry that lubricates. Graphite fits that. Because graphite, When it gets caught between two things, those layers can slide across each other. And so they don't get stuck. So it's a dry lubricant because the pieces can slide. Okay. Now, you'll notice that I had a whole bunch of, in order to have trigonal planar, I got to have double bonds, which means I have electrons between these two, pi bonds. The pi bond from this molecule interacts with the pi bond from that molecule. Okay. Which means those pi bonds can be anywhere. Which means electrons can be anywhere. Which means graphite conducts electricity. Diamond doesn't. Okay. Diamond, all my electrons are in sigma bonds trapped between the two atoms. They can't go anywhere. Here, the pi bonds in between the layers allow electricity to flow. And you'd think that would be all about it. You'd have that or that. But actually, if you take just one of these sheets, it's a new material they're really interested in working on. It's got some great properties. It's called graphene. So if you hear about graphene, it's just one layer of graphite, a big flat sheet. If you want a sheet of graphene, just put tape around a pencil and pull it off. It'll pull a layer of graphite with it. And you've just made a layer of graphene. You think that would be all the possibilities, but it's not. Okay? Actually, those were all the possibilities. There's a third one called soot, and soot is no pattern, just randomly hooked to each other. Sometimes sometimes trigonal pyramidal, sometimes tetrahedral. So soot has no pattern. Okay? And those are the only three they knew about when I started high school. Then, when I was in high school, they found these new shapes called fullerenes. And fullerenes are little spheres, like a soccer ball. But they're all covalently bonded. Okay. What's interesting with this is they can get these to cross the blood-brain barrier. So they're thinking about putting things inside these fullerenes. And then when they get inside, tear them apart and get that, so you can get a drug across into the brain that you couldn't get any other way. So fullerene. This is one, I think this one's C50, there's a C60, there's a C120, there's like three of them. Where you get the right pattern, they fit together just right, you get a fullerene. Although the official name is fullerene because it was named after a guy who made the geodesic domes in the 60s. Those angle-shaped domes, those are called geodesic. The guy who just was big on those was Buckminster Fuller. So that's why they're called fullerenes, because his last name was Fuller. But every chemist refers to them as buckyballs from Buckminster. Buckyballs. You still think that would be all the possibilities, but it's not. Okay? Like, what? How can that not be all the possibilities? Well, they took one of those layers of graphene and where'd it go? Where's my other one at? I had it here. Let me search for it again. Got closed someplace. Okay, it's called a carbon nanotube. Okay, a carbon nanotube. Say, why would you call it a tube? Because it's a tube. Okay? It's a tube. Actually, this is a tube inside a tube. There's several different kinds. This is a small one. It's a tube. But you'll notice what it is it's a whole bunch of carbons hooked three at a time. So it's all trigonal planars hooked together. So all they did was take a sheet of that graphene and wrap it all the way around. Okay? What they're looking at using this for is really strong rope. Okay? You say, well, why would that make really strong rope? Well, in order to break these, you have to break bonds. In other ropes, you just have to overcome intermolecular forces. They think they could make a rope strong enough with this, they could make it long enough that they could build an elevator to space. You just have to have a rope that can hold 22,000 miles of its own weight. This could do it. because you got to get up to geosynchronous orbit, which is 22,000 miles away.
Why'd you want to build a rope to space though?
Because if you take an elevator into space, you don't have to fight friction, so you can just put the rocket on the elevator piece by piece and not burn all that fuel fighting the air friction going through the rocket. You can get rockets up into space and launch them from up there without having to fight the atmosphere or the gravity, because you're already moving 25,000 miles an hour when you get out there. So going up also makes you go fast, because you're at the end of something that's spinning around. So it would make space travel much easier to have an elevator in space. You just got to have the materials to do it. Yeah. And like I said, glass. Okay. Covalent bonds are much stronger than intermolecular forces, so network solids are hard, and they have high melting points. The other place that you like to use, where you hear graphite being used is in golf clubs, baseball bats, car bodies. They just layer pieces against each other and then put one so they can't slide.